So, today we will discuss about the polarization of light and we demonstrate some experiments on polarization. So, let me just tell you about the polarization of light. So, light is an electromagnetic wave, so that is well known to all of us. So, this it has basically two component, electric field component and magnetic field component, and these two components are mutually perpendicular to each other, and also these two components are perpendicular to the direction of propagation, That means this electric field component, magnetic field component and direction of propagation, they are mutually perpendicular, right. So, this is the electric field component, okay. It's basically its amplitude, this is the amplitude, these are varying like wave, right. And magnetic component also there's varying like wave, right. So, now this magnetic component actually its strength is very weak compared to electric component, okay. So, for electric interaction with matter, generally we neglect, we ignore the magnetic component. So, that means it is just like this light, we can treat as a like this, okay. It has electric component and it is varying, okay. So, actually magnetic component also varying in the same way, because they have to maintain the mutually perpendicular with each other. So, it is in perpendicular plane, okay. So, we are neglecting that part. So, we can think that, okay, light is propagating in this direction and it has electric component, it is varying like this, right. So, this electric component actually it's the rotating, it's the rotating. So, this it's then it's changing the direction, right, again. So, it's this electric component is rotating on a plane perpendicular to the direction of propagation. So, electric component in as if in all direction on a plane perpendicular to the direction of propagation, okay. So, this type of light where electric component is vibrating in all direction, on a plane perpendicular to the direction of propagation. So, this type of light is called unpolarized light. This type of light is called unpolarized light, okay. So, this unpolarized light generally we represent like this. So, this is the direction of propagation, and so it is in all directions. So, these are basically vectors. For any direction you can get two component, okay. You can get two component mutually perpendicular two component. You can resolve any vector into two component, okay. One is they are mutually perpendicular, okay. Any vector you will get two components. So, whatever the direction, so we can think that so this we can represent with the component in two directions, okay. Component in two direction was in this direction and another is perpendicular to these papers, okay, because this is the direction of propagation. So, this line as well as the dot here, okay. See, the dot means this electric component is perpendicular on the plane of the paper. So, this way we represent the unpolarized light. Okay. Now, if only one component exists and other one is removed by some means, then we tell this is the polarized light. Okay. So, if this direction is fixed of this electric component, okay, it is in this direction by some means, if we can fix it, then we tell this is the polarized light, or it can be, so other component is there and this component is removed by some means. So, we can represent this either this or that one is polarized light. Okay. So, only is a electric component will have a fixed direction, then it is polarized light, right. So, electromagnetic wave, so that wave we can represent this, the y is a function of xt, this is the x direction and this is the y direction, electric component vibration in y direction, and this is the z direction for h. So, for electric component, okay, y is basically electric component. So, it will vary following this equation. Okay. So, there is A is basically E0 maximum amplitude. Okay. So, A sin kx minus omega t. So, this is the general equation of waves, okay, where this omega is the basically is related with the time period t equal to 2 pi by omega, and this lambda, this is the lambda. Okay. So, it is a k is wave vector, or we tell momentum vector. So, this k is equal to 2 pi by lambda. Okay. So, here k and omega is actually they are related with the momentum vector and the time period. Okay. So, now polarized, unpolarized light, by some means if you can make it polarized. Okay. So, different types of polarization one can get. So, what are those? These types? This one type is called the linearly polarized light or plane polarized light. Okay. Linearly polarized light or plane polarized light. So, these are basically, it's this is called linearly polarized light, this or that. Okay. So, it's a electric vector, it's vibrating in a particular direction with constant amplitude, okay, with constant amplitude. So, then it is the polarized light, linearly polarized light. So, it can be this way, it can be this in this way, or it can be any direction, but it will maintain that direction and it will maintain the amplitude. Okay. So, this called the linearly polarized light. Also, there are other two types, circularly polarized light and elliptically polarized light. When the tip of this electric vector, it will rotate on a circle, okay, then we tell that this is the circularly polarized light. If it rotates on a ellipse, tip of the electric vector, if it rotates on a ellipse, then we tell that is the on a ellipse, basically this is the ellipse. So, then we tell that this is the elliptically polarized light. Now, rotation, it can be clockwise, it can be anti-clockwise. Okay. So, if it is clockwise, so it is clockwise. So, this my right hand, so right-handed polarized light. If it is anti-clockwise, it is towards my left hand, so it is called left-handed polarized light. Okay. Left circularly polarized light or left elliptically polarized light. Okay. So, these are the type of polarization. So, here what about the, so one can identify whether it is linearly polarized light, whether it is circular polarized light, whether it is elliptical polarized light, how to distinguish them. So, experimentally one can find out. So, next for polarization, as I told, this how to make, how to get the polarized light. So, generally natural light is unpolarized light, natural light is unpolarized light, and to get the polarized light you need device, you need some device, you need some arrangement. So, what are the devices for polarizing and analyzing light? So, you have to polarize the light, and whether it is polarized or not, that also you have to analyze, right. So, that is why we tell polarizing and analyzing of light. So, device for that is a very common device in laboratory we use, that is basically called polarizer and analyzer. Basically polarizer and analyzer both are same device, okay. But depending on the use of that, we tell the it is the polarizer when it is polarizing the light, and then it is polarize the light, okay. Then after polarization, if we want to analyze whether it is polarized or not or whatever about the information of polarization, okay. If you want to know, so we use the same polarizer, but then we tell that says the analyzer. So, what is polarizer? In simple way, we can tell that it's a basically it's a made in such a way, it's made in such a way, it's the plate kind of things. It is made in such a way that this it has a axis, is called optics axis or pass axis. Electric component only pass through this pass when it is parallel to the optics axis. So, electric component which is parallel to the optics axis, that only will pass through this polarizer. Other components will not be able to pass through it, okay. So, electric component is a basically vector, it is a basically vector, right. So, if I place a polarizer, its optics axis is parallel to this component. So, other side of the polarizer I will get light, only this component will be there. So, then it is a polarized light. Or if I put in such a way that this optics axis is parallel to this, then this component will not be there, only this dot components will be there, then also it is polarized light, okay. So, now this is the polarized light. So, electric component is along this direction, and its magnitude is constant, right. Now, if I take another polarizer for analyzing this polarizing light, so this basically you can tell this it is the analyzer, okay. So, if you put this polarizer or analyzer after this polarizing light, so this light will enter into this polarizer or analyzer, okay. Now, optics axis of this polarizer, of this analyzer, if it is parallel to the optics axis of this polarizer, okay, that means this optics axis is parallel to the electric component, right. So, then this electric component easily should pass through the polarizer, this analyzer, right. So, I should get the same intensity of light on the other side, right. Now, if I rotate this polarizer, this analyzer with angle theta, then this component basically will make angle theta with this optics axis. So, only electric component parallel to the optics axis will pass through it, right. So, we can say that if this is E, so E cos theta, that component will be parallel to this optics axis. So, E cos theta will pass through it. Okay. So, if I vary this angle, when it will be 90 degree, so E cos theta, E cos 90 degree will be 0, right. So, I should not get any light on the other side, right. So, basically whatever E here, polarized light, it is falling on the analyzer. Okay. Now, optics axis of the analyzer, if we change this theta angle, so E cos theta, that will be the component which will be parallel to this optics axis and that will pass through. So, this is the electric component, right. Square of it is basically intensity. E square equal to say I0. So, this E cos theta square is I. So, I equal to basically I0 cos square theta. So, other side intensity should follow this relation. Okay. So, intensity will change as a function of cos square theta. Okay. So, this intensity of light varies following this I equal to I0 cos square theta. So, this is called Malus law. Okay. This is called Malus law. So, now we will demonstrate this experiment, verification of Malus law, whether Malus law follows or not. So, what we will do? We will basically measure the intensity, we will measure the intensity I, okay, of light from this arrangement, okay. And if I plot, I will change the angle I versus theta. So, cos theta, you know, this change like this, okay, cos square theta. So, this it will change like this. It will change like this, cos square theta. Okay. So, this I basically is a cos square theta and some initial I0 will be there. When theta equal to 0, when theta equal to 0, so this value basically I0, right. Now, it is the basically it's a 90 degree, this is 0 degree, then this will be 180, 270 and this will be add 45. So, 135, this angle will be 135, then this will be 180, 45, 225, right, 225. So, I should get maximum light at 0 degree, okay, parallel to the optics axis, and then 90 degree it should be 0. So, what we will do this experiment? So, we will change the angle by 10 degree or 20 degree, okay. 10 degree I should change by 10 degree, okay. So, then you will get this point, and if you plot, then this type of curve you should get, okay. So, let us do the experiment. Let us let me show you the experimental setup. So, this is the simple experimental setup to verify the Malus law. Okay. So, here actually this laser, this diode laser, this is the diode laser. Okay. So, this is the power supply of the laser, this is the power supply of this laser. Okay. It is on. So, light is coming out from this laser, point light. Okay. Now, this light generally from laser light are polarized light. Okay. Laser light is polarized light. So, I do not need to polarize it. Okay. So, as I told, this polarizer or analyzer. So, this is the polarizer. So, inside you are seeing this one circular plate. So, this is the polarizer, and outside you are seeing the circular scale. Okay. So, this is, you see, one mark is here, one mark is here. Okay. So, now it is at 0, now it is at 0. Okay. Now, I am changing. So, so it is at 0. So, this is the polarizer, means it has optics axis. Now, optics axis I do not know in which direction, it can be in this direction or it can be in this direction, whatever, it is fixed. Okay. Now, I am rotating the polarizer, I am rotating the polarizer means I am rotating the optic axis. So, it was 0, now I am changing to 20, then it is going 30, then 40, 50, 60. So, that way I can change, up to 360 degree. Now, it is 180 degree, now it is at 180 degree. Okay. So, this way I can get a one complete rotation. I have come back to, that means I have arrangement here to rotate the optics axis, and that angle I can measure, right. So, the same thing we have put here. So, I am not going to disturb this one. So, same this thing we have put here. So, this light is coming, if it is not polarized light. So, what I could do, so it is a light source, and then I could put this polarizer here. Okay, I could put this polarizer here, then it will be polarized light. So, but that is not necessary since we are using the laser light. Okay, it is a polarized light, linearly polarized light. Okay. So, this linearly polarized light is falling on the polarizer. So, this will use as a analyzer. Okay. So, polarized light, linearly polarized light is falling on this polarizer. So, we have set optics axis parallel to this electric component of this polarized light. Okay. How I will know this is a parallel, right, and how I will measure the intensity of light. So, light is coming and falling on it. So, it is basically it is the photo detector. It can detect, it can I think I can show you the spot of the light. Yes, spot of the light you can see. So, inside, basically inside there is a detector, and one, I do not know whether you can see or not, there is a small hole. So, through that hole this light is falling on the detector. Okay. It's a, what is that detector? It's a very simple, it's the photodiode basically. I can explain you the I can explain you the principle of this photodiode. Actually, you know diode, this PN junction, say PN junction. Okay. So, this is P and this is N. Okay. PN junction diode, PN junction diode. Now, there is a depletion layer, between this at the junction, right, at the junction, this is a depletion layer. Okay. Now, if we apply reverse bias, reverse bias means, so this P will be connected to the negative terminal of the battery and N will be connected to the positive terminal of the battery, right. Now, if you apply this reverse bias, so what will happen? So, this depletion layer, this width will be bigger. So, it will be like this, So, this is P, this is N and this is the depletion layer, Okay. So, now depletion layer is the larger area. So, when this light is falling on this diode, okay, so it will fall on this diode. So light is falling on this diode, okay, it will generate electron and hole, okay, it will generate electron and hole. How many electron and hole it will produce? That is proportional to the intensity of light. Okay. Now, this electron, so from here, if you measure the current, okay, so this current, so this electron and hole, they will move, okay, they will travel, so it will give current, okay. So that current will be proportional to the concentration of the pair generated, production of the electron hole pair in this depletion layer. If it is produced in other region, what will happen? There will be recombination, you know. So you will not get current for this for that pairs. So that's why we increase the depletion layer. So there is no hole and electron. Okay. So whatever hole and electron will produce, they will not recombine. They will move in opposite direction and give current. So so this current will be proportional to this pair, density of pair, concentration of pair, and concentration of pair is proportional to the intensity of light falling on it. So this current, whatever you will get, that is basically proportional to the intensity of light. Okay. So this current we can take as a intensity of light. Fine. So that is the principle, working principle of this photodiode. Okay. So this photodiode we are using as for measuring the intensity of light in terms of current. Okay. So now what I will do? So this polarizer, this is analyzer. So I will change. Now we can see. So I have to take reading. Here itself I can tell you. So I have to see the reading of the. I think we can show the reading. So here you can see this, my marker is at 20, I think 25, it is at 25, yes. Each division is 2 degree, so it is at 25, fine. So now, so this I have set. So this angle theta, okay. this is the initial angle, or this is a reading, is not angle theta, is the reading of analyzer, reading of analyzer, okay, reading of analyzer, okay. So initial reading, so it's we are writing that is the theta 0, it is a 25 degree, okay. And you can see this meter, is a current meter, right. So connection you can see, it is coming from the from this photodiode, it is coming from the photodiode, okay, this current. So it's giving the reading, it's a 30.2, okay. So actually I have set it at a highest current, that means whatever the light passing through this analyzer, that is the highest intensity of light, and that is coming at 25 degrees. So you can say that this axis, optics axis, the reading this optics axis, okay, which is parallel to the electric component, this is optics axis, okay. This optics axis is parallel to the electric component, okay. So at this position, so this theta 0, we are telling theta 0 is the 25 degree. So that means from other angle, so this we can take as a 0 angle, is the parallel. So whatever in formula I have showed you, this angle between the optics axis and the electric component, so this angle is theta, okay. So this angle theta, I can tell this angle theta is basically whatever reading you are taking, so that whatever reading you will get, so that from there, so now it is 25 minus theta 0, theta 0 is 25, so it is the 0 degree. So at 0 degree, what is the reading of the current? 30.2, 30.2. It is in milliampere. There you can see there are two option, microampere and milliampere. So we have kept it at milliampere. So current is 30.2. Okay. Now I will change the angle. By 10 or 20 degree. It is at 25. So now you can look at this, when I will rotate, you can look at this current, how intensity is varying, means current is varying. So I put at now, say it is 25, let me put at 40, okay. It's now at 40 degree and 28.9. So I have to note down, it's a 40 degree minus your theta 0. So basically it's a 15 degree. So our theta is 15 degree. For that you are getting reading 28.9. Okay. Next I will change to 40 to say 50. I will change 40 to 50. So now it is 26.2. Okay, 26.2. So it's a basically 25 degree, because reading is 50 minus 25 is the 25 degree. So this way I will vary. So now it is at 50 minus theta 0 means 25 degree. Okay, 25 degree. So this way you vary and note down the reading. So I am not going to note down the reading. Just let me show you that now it is at it is at 50, then I am going to 60, take reading 23.8, note down, then I am going to 70, 19.1, that reading you should note down, then I am going to 90, okay, is 13.0. So, here reading 90 means 90 minus 25, okay, 90 minus 25, okay. So, that is the theta. So, if I go 100, so it is the 4.6. Now, I am going 110, it is a 0.9. Now, I am going to 115, yes, yes, it's not 115, it's slightly higher than that, it's around, yeah, around 200, okay. So, around 200 I am getting the around 200, this reading is a 200. So, you take reading at 200 minus theta 0 means 25, okay. So, around not 200, it's a, sorry, it's a 120, yes, 120, not 200, 120, okay. So, minus 20 is a 95 degree, okay. So, it should come that 0 intensity, 0 current we are getting at 95. So, there is some error, okay. So, one should repeat the experiment, okay. So, it's the 95. So, it is supposed to be 90. So, one has to do very carefully. So, then it should come. So, I will continue by again I am going 120 to 130. Now, started to increase is 0.5, 140, 2.6, reading is 2.6, 150, 6.5, 160, okay, 12.2, 170, 16.9, 180, 22.2, 200, it is the 28.7, then 200. So, I am getting maximum at this point. Now, again started to decrease. So, let me maximize it, okay. So, I am getting around this 220, okay, 220. So, 220 I am getting again minus 25. So, it will be 195, 195, okay. So, I am getting again maximum, okay. So, it is supposed to be at 180 degree, it is supposed to be 180 degree. It may happen that when initial reading I was taking, there may be mistake, it will be maybe not 25, okay. So, I will check when I will come back, I will check it. So, this way, so all the time I am getting positive current, you know. So, this is the current equivalent to intensity of light, this is the theta. So, it is varying 0 degree maximum, and then I am getting at 95, it is supposed to be 90, 0, and then it is changing, again I am getting maximum here, okay. So, I am up to this. So, I can continue 360 degree, and let me come back to the 0 initial position. So, now I am at 240, decreasing again 260, decreasing 280, more or less 4.5, then it is uh, 2 300, I guess. Is the 300? Yes, it's almost 0. 300 is almost 0. Okay. Again 320 increasing, 340 increasing, 260 means 0, then 220 sorry 360, then that means 0, that means repeated again these are 20. So then I am changing it is yes, it is around 30. Yes, it's a 30, around 30. Okay. So that again you take this one. So actually this 25 whatever I took, so it will be 30, it will be 30 degree. So initial reading probably I took wrong. So now it's you can see that maximum we are getting when it is at 30. Okay. So instead of 25, you can subtract 30. Okay. So then it will be 90. Okay, it's 30, then it will be 190. So some slight error will be there. So that's why we draw graph. So there will be graph will not be, so there should be average graph. Then you will see that it is following the cos square graph. You know cos, this is the cos graph. Okay, this is the uh, cos theta graph. When you will square it, so this part basically it come up, it's come up. Okay, square of it, so negative part will not be there, so you will get this type of curve. Okay, so intensity of light, polarized light, intensity of polarized light making angle with the optics axis of the polarizer or analyzer. Okay, if it is theta, so this intensity is varying following the cos square theta formula, following the cos square theta, and that is the Malus law. And this is the verification of Malus law. Okay, so these are very simple experiment of polarization, and hopefully I was able to explain you properly. Only here, since it is polarized, so I do not need to polarize it from the natural light. So if necessary, if you use natural light, so here difficulties is that we need higher intensity for doing this experiment, otherwise you will not get current there, sufficient current. So that's why we have used the laser beam. Okay. So I will stop here. Thank you.